Inductance calculation. So before going for calculating the inductance of the transmission line, we should know the basic things, how the inductance forms in the transmission line and what are all the basic formula for that one. Already we may know some terms, so we will refresh those terms. This is psi, flux linkage psi, magnetomotive force MMF, magnetic field strength H, and the Hx we can say as magnetic field strength enclosed in the circular path. Ix is the algebraic sum of current density enclosed in the same circular path, and Bx is the flux density. Normally B they will call it as flux density, and Bx means again the flux density in the same circular path. We will just think about what is meant by inductance. Inductance, we know the formula L is equal to flux linkage by current. The flux linked on the conductor, either it may be an internal or it may be an external of the conductor, upon the current flowing through the conductor. So how this inductance forms and what are all the factors it depends upon. Basically, the formation of inductance, it depends upon the material of the conductor, size, position of the conductor. If we are having number of conductors, then what is the position of each and every conductor, what is the distance, again the same thing, spacing of the conductor. So these are all the main factors for forming an inductance in the conductors. So how to calculate this inductance means we are having a three form in order to calculate the inductance through the flux linkage. So flux linkage due to wound conductor current, both in internal and external term, and not only because of the flux linkage internal external of the same conductor, also because of the neighbor conductors. So the flux linkage due to other conductor currents. So if we know these three flux linkages, then we can easily calculate the total net flux linkage of any conductor, and from that we can calculate the value of inductance. First we will just see the flux linkage due to internal flux and flux linkages due to external flux because of the current carrying on the same conductor. So now consider a conductor, cross-sectional view of the conductor. Say radius of the conductor is r meters. It may be a centimeter or meter or even a millimeter. Among this cross-sectional area, just consider a small cross circular path. Say that radius is x meter from the center of the conductor and thickness of the conductor is dx. Now for this circular path, we have to assume the current is flowing on that conductor surface on the small circular path, and what will be its magnetic flux linkage and all we are going to assume. For this we have to think about the Ampere's law as well as the Maxwell's equation. So the Ampere's law, what it says, in any closed path, the magnetomotive force MMF is equal to current enclosed on the circular path. So MMF equal to Ix, that is current density into area. So this current density we can say I by pi r square into pi x square. So from this, if we simplify, we will get I by r square into x square. This is by Ampere's law. Now we will again realize through Maxwell's equation. The same MMF is equal to line integral of magnetic field intensity. So we can say line integral of hx into dl. So this we can represent as 2 pi x into h. If these two MMFs, if we equate, then we will get the final equation as h equal to I into x by 2 pi r square ampere turns per meter. We are calculating the field strength. Magnetic field strength is equal to I into x by 2 pi r square. That means the magnetic field strength depends upon the current flowing through the conductor in the circular path as well as the radius of the conductor. Even we are considering the small circular path, so that the x term it shows. Now from this magnetic field intensity, now we are going to calculate the flux density B. Flux density B equal to mu H. Mu is the permittivity of the conductor, and we can say mu naught mu R. For non-magnetic material, mu R equal to 1. So directly we can substitute, instead of mu naught and mu R, we can neglect the mu R value and simply we can put mu naught. So flux density equal to mu into H, that is equal to mu equal to Ix by 2 pi r square Weber per meter square. So what is the flux linkage on the considered smaller circular path? d phi is equal to flux density into area of the circular path. We can say the flux density already we have calculated, B into that area is del A. The del A we can represent, the del x is the width of the conductor that considered circular path, and we have to consider for a unit length. So the unit length here we are substituting 1. So if we see that if we substitute the value for B in terms of h, then we will get mu Ix dx by 2 pi r square. This equation is nothing but called as flux linkage on the circular path because of that current flowing on the circular path. Now we are having only a small portion of circular path on the conductor. If we integrate with from the value of 0 to radius r, then we will get the complete flux linkage of the internal conductor. So let's say the final equation here is the flux linkage d psi equal to pi x square by pi r square d phi, and this we can finally get the equation mu I x cube dx by 2 pi r to the power 4 Weber turns per meter. This is the final expression for the circular path magnetic flux linkage. Now we have to apply the limits. So now the flux linkage due to single current carrying conductor. Just imagine there is a conductor and current is flowing through the conductor, and as we consider a small circular path at x distance from the center of the conductor, and the radius of the conductor is r meters. Now as I initially said, once the current is flowing through the conductor, there will be a magnetic flux set up on the conductor. The magnetic flux links on the internal part of the conductor as well as outermost outside of your conductor also. So we can say that internal magnetic flux linkage as well as external magnetic flux linkage, we can split into two forms. This magnetic flux linkage we can split into two forms. One is internal magnetic flux linkage and the next one is external magnetic flux linkage. This internal magnetic flux linkage we have to say from 0 to radius r, and external magnetic flux linkage we have to consider from r distance to infinity. Now we are going to see for flux linkage due to internal flux alone. So right now we have calculated the value for the circular path of the conductor, a small portion dx width. So this is the internal portion of the conductor. So now we are going to calculate for internal flux linkage. As already we have said that the flux linkage d psi for the circular path is mu I x cube by 2 pi r to the power 4 dx, and now this value, if we integrate with the limit of 0 to r, then we will get the final result as mu naught I by 8 pi Weber turns per meter. So if you see here, the flux internal linkage, psi is the flux linkage symbol, so psi internal equal to integral of 0 to r mu naught I x cube by 2 pi r to the power 4 dx. Then if we solve this, among this, if you say this mu naught I 2 pi r to the power 4 are all constant, and only we are having x cube by dx. If we apply the limits 0 to r to this x cube, then we will get the solution flux linkage internal equal to mu naught I divided by 8 pi Weber turns per meter. Further, if we want to reduce this equation, then we can substitute the value of mu naught in place, mu naught equal to 4 pi into 10 to the power minus 7. If we substitute that one, then the internal magnetic flux linkage equal to simply I divided by 2 into 10 to the power minus 7 Weber turns per meter. We know very well inductance L equal to psi by I. Again, if we substitute, then we will get 1 divided by 2 into 10 to the power minus 7. That's a constant value for internal flux linkage. Now we have to see the flux linkage for external, the total net flux linkage in the external side, that is from distance r to infinity. So for this case, again we have to calculate, we have to consider a circular path on the external side, and that distance is x meters from the conductor, and dx is the width of that considered circular path. So again we have to go back to for calculating the flux linkage on that circular path. So here the same thing, the magnetic field strength equal to I by 2 pi x ampere turns per meter. The same way flux density mu into h, that is mu I by 2 pi x Weber per meter square. So from this we can easily calculate the flux linkage on that circular path. It's simply mu I by 2 pi x into dx, and this is your flux density and this is your area, and we know we have calculated for unit length. The net total flux linkage on that circular path is d psi equal to mu naught I dx by 2 pi x. So this is the final value expression for your considered circular path. Now we have to integrate this value with the limits of r to infinity in order to get the complete flux linkage on the external side. So now the psi external equal to integral r to infinity mu naught I by 2 pi x dx, as we derived there. So this one we can able to take some constants outside. This mu naught I 2 pi, these four terms are all constant, so we can simply take it out, and our equation becomes mu naught I by 2 pi integral of r to infinity dx by x Weber turns per meter. And from this is the final expression for the external flux linkage from distance r to infinity. Now we got both the values, internal flux linkage as well as external flux linkage. Now if you want to calculate the net flux linkage on the conductor because of current flowing through the conductor, same conductor. The net total flux linkage psi equal to psi internal plus psi external equal to mu naught I by 2 pi into 1 by 4 plus integral of r to infinity dx by x Weber turns per meter. So this is the final expression for the magnetic flux linkage on the conductor because of the current flowing through the same conductor. Up to this, the solution is not completed because in the transmission line we are not having only one conductor. There are many conductors are there. For example, if it is a three-phase transmission system, then we may have 3 conductors. Because of the current flowing in all the 3 conductors, the magnetic flux, external magnetic flux created from the neighbor conductors that may disturb the conductor of your original. So now it's essential to calculate how much disturbance from other conductors. So how to calculate for that one? So if you see the flux linkage in parallel conductor, that means the neighbor conductors. So how this will be? So if you say that if you are going to calculate the flux linkage on A, we know already we have derived that if the current IA is flowing through this conductor A, then the flux linkage internal as well as external we already solved, and that is not sufficient in order to calculate the complete inductance of conductor A, because also there will be a disturbance because of current IB, IC, ID, IE and IF, that which it flows on the respective conductors B, C, D, E, F. So only we have to consider the external fluxes of those conductors, those remaining conductors, because internal fluxes will not affect that one. Your external fluxes that spread from the distance of the conductor to your infinity place. So that we have to consider here. Now consider this diagram, and if you see here we are having a 6 conductors and the distance between the conductor A to B is D1, and from A to C is D2, and from A to D is D5, like that it goes on. Now just we will see how to calculate the magnetic flux linkage on conductor A because of conductor B, that is because of current flowing in conductor B, IB current. So now come to here, flux linkage with conductor A due to current IB. Psi AB, this psi AB represents flux linkage in conductor A because of current IB, equal to integral of D1 to infinity. We know very well D1 is the distance between your conductor A and B. Integral D1 to infinity mu naught IB by 2 pi x dx. So now the current, your flux is because of current IB. That's why here we are marking IB. So now if you see here again, mu naught IB by 2 pi is the constant value. If you simplify, we will get mu naught IB by 2 pi integral of D1 to infinity dx by x. In the same way, if we go for calculating the magnetic flux linkage with conductor A because of current IC, that means because of current C, conductor C, psi AC equal to integral D2 to infinity. That means the distance from A to C is D2. D2 to infinity mu naught IC by 2 pi x dx, and again the same equation we will get. So now if you see for remaining all other conductors, or if there is n number of conductors are there, depends upon the distance as well as the respective current flowing on that conductor, your magnetic flux will affect. So if you see here, in conductor B as well as in conductor C, IB current as well as IC current flows, and that set up some magnetic flux in the external part, and that external part disturbs the magnetic flux on conductor A. So because of this issue, the net magnetic flux linkage on conductor A is psi is equal to mu naught Ia by 2 pi into 1 by 4 plus integral of r to infinity dx by x. This is because of your current Ia, both internal external, plus the magnetic flux linkage because of current IB and magnetic flux linkage, external magnetic flux linkage of current IC, and so on. If n number of conductors are there, then n number of current, that equation you have to write, and you have to calculate the total net flux linkage on conductor A. So up to this we have calculated the total magnetic flux linkage, how it forms, and what are all the factor it contributes to create the net magnetic flux linkage. Once if we know, then we can simply calculate the inductance L equal to total magnetic flux linkage by the current which it flows through this conductor.